Hello and welcome to another computational geometry video. Today we're going to be switching it up and talking exclusively about some theory, specifically regarding the hidden set problem. We're going to be basing the content of this video primarily off of the work of Thomas Shermer, specifically in his 1989 paper, Hiding People in Polygons. So before we get into hidden set, we have to describe the general realm of visibility, specifically visibility within the two-dimensional plane. So visibility is defined with respect to 2 points. So a point is visible from another point if and only if the line segment between those 2 points is fully contained within whatever polygonal domain we're dealing with. So in this case we have a polygon. It's a convex quadrilateral, and if you take that line segment between those 2 points, the line segment exits the polygon before entering again in between the 2 points. Therefore, it can be said that those 2 points are hidden from each other, or not visible. Whereas if we added this third point, that third point is visible from both of the points and is then said to be seen from those 2 points. Using these visibility relations, we can define a graph between sets of points within a polygon. This graph is known as a point visibility graph. In particular, we'll be discussing the infinite variety of a point visibility graph, that being an infinite graph constructed in this way from all of the points within the polygon, which is more of a thought experiment. Obviously, it's infinite size, so we can't make the entire graph in any practical application, but it is an extremely useful notion in order to describe problems such as the one we're going to talk about today. So in a point visibility graph, 2 points, or in this case translated to nodes, have edges between them if the points that correspond to those nodes within the polygon see each other. So these 3 points corresponded to the three previous points. These 3 nodes correspond to the 3 previous points, and the relationships in terms of hiddenness and seenness or visibility are preserved. So within this graph setting, a hidden set, or a set of points which are hidden from each other, is the same as independent set within the infinite point visibility graph. An example, well, 2 examples of hidden sets include the one on the right, which is just a single point within a convex polygon, and we'll get into why that's a special case in a little bit. And on the left, we have a hidden set within just a random polygon to kind of get to the point. So as you can see, if you drew any line segments between any of those 2 points, any 2 of those points, any pair you choose, that line segment would go outside of the polygon. As a result, the set of points is referred to as a hidden set. Now that hidden set is not maximum. It is not the maximum amount for that polygon. We could do it out, but it's not the maximum possible. That takes a little bit of care in improving for a given polygon. But for convex polygons, it's easy. By definition, a convex region has the line segment between 2 points is contained within that region. Therefore, all points within a convex region are mutually seen from each other. And that's going to come up in importance later with respect to finding the maximum hidden set. So in a convex polygon, the maximum hidden set is just any point in there, 1, because if you add another point, it would necessarily be seen by all the other, any point that you had previously added in. Now we're going to go into the realm of combinatorial bounds. So that's looking just at the number of vertices or reflex vertices. How big can the hidden set get? So with respect to reflex vertices, those are vertices where the angle made by the two sides before it and after it, if that angle is greater, well, the one side before and after. Anyways, if that angle is greater than 180 degrees, that vertex is referred to as reflex. So for hidden set, it can be at most the number of reflex vertices plus 1 in the general case of all polygons. And that's shown on the left here with a fan. Shermer uses the exact same idea in his paper, where you take a fan, you put one point at each of those edges, and they're all mutually hidden from each other. And this bound of the reflex vertices plus 1 translates to just n being the total number of points in the polygon, the combinatorial bound with respect to that. And that comes simply from the fact that there must be at least 3 convex vertices. So in the case on the left, we have exactly 3 convex vertices, and the rest are reflex vertices. That means that there is n minus 3 reflex vertices. N minus 3 plus 1 is n minus 2. There's also combinatorial bounds specifically within the domain of orthogonal polygons. Those are polygons where every angle is either 270 degrees or 90 degrees. So it remains the same in terms of reflex vertices. So the number of reflex vertices plus 1 is an upper bound on the hidden set in a tight upper bound. In terms of it's realized in our example here of the staircase on the left, that is a tight upper bound for the size of the hidden set in orthogonal polygons. However, if we take it to the general case of all vertices, n, our maximum number of reflex vertices that we're able to obtain in an orthogonal polygon is constrained down to n minus 2 over 2. Meaning that we're constrained in that way. That the hidden set in an orthogonal polygon must be less than or equal to n minus 2 over 2. Now I'm going to go over 2 cases in which we have known polynomial time algorithms to find the hidden set. The first one is spirals. And the spiral algorithm actually was found by Bajuelos et al. And it basically entails grabbing all the reflex vertices in that reflex chain. By definition, a spiral polygon has a reflex chain and a convex chain, no intermingling of the convex and reflex vertices. So you just plop a hidden point on each of those edges in the reflex chain, and by definition, they will not see each other. Now the other example is in histograms. In the general case, an algorithm that me and my friend Eric Chu developed is used. The previous paper also had a variant, I believe, of their paper in which they had an algorithm, but it only worked in the general position case. Our algorithm includes the ability to find it when there are collinearities. And the idea is the red points below are the hidden set. You place them at all the midpoints of all these horizontal edges, except for the cases where those midpoints come into conflict with a previous horizontal edge, such as in the blue point case. And in those cases, we don't add those to the hidden set. And we're able to keep track of that using a stack in terms of what are the possible conflicts. So using a similar argument to the Gram scan, we are able to argue that we have an O of n time algorithm. Here's a little overview of the state of the problem in terms of hardness. So in terms of the domain of simple polygons, the hidden set problem is APX hard, and that was proven by Eidenbenz in a paper called in 2002 called Inapproximability of Finding Maximum Hidden Sets on Polygons and Terrains. For the general case of terrains, that's also APX hard. For polygons with holes, it is APX hard from simple polygons, but there was a previous proof as well for that case. So yeah, so that's the general overview of hardness. Because this is primarily focusing on the Shermer paper, I'm not going to go over the Eidenbenz proof, or I should say reduction, to APX hardness, but I will go over the Shermer reduction. So Shermer's reduction regards NP hardness, and it's a reduction from 3 satisfiability. So for those of you unfamiliar with hardness reductions, you take a known problem, which is NP hard, and you show that if there were a polynomial time algorithm for the given problem that you're trying to prove hardness of, then it would imply that there is a polynomial time algorithm for the previous, the known NP hard problem. So in this case, we're dealing with 3 satisfiability, which is a classic hardness reduction problem. So there's 3 components within the hardness proof in terms of gadgets. So those are going to be little polygonal pieces that are added in to construct an instance. And yeah, so the main components are going to be literal units, which represent the literals in the 3 sat instances, clause units, which represent the clauses of the 3 sat instance, and an additional structure known as a consistency checker, which is used to make sure that truth assignments, so in 3 satisfiability, you're trying to satisfy a set of constraints. Those consistency checkers are going to make sure that your literals are either set to true or set to false, and that within a variable, which the literal is an iteration of, that the positive case is either true or false, and then the negative case is either false or true. So they have to be opposite of each other. First component is the literal units, and so the literal units are supposed to represent either on the top case a variable, meaning the variable itself not negated, and then the bottom is the opposite of the variable, so the variable has to be false in order to come up true in the satisfiability in the clause. So the first instance, the literal unit, so there's going to be for every clause, right, that the literal is going to show up in at most n, which is all of the clauses. So it's going to have little bumps up there to represent all the clauses that it might be a part of. And if it's not in a clause, it still is going to have that bump. It's just the bump can be made a little less carefully. So it has top bumps and bottom bumps, with the bottom bumps representing an assignment of true. So if the variable is set to true, then the literal unit on the left will have all the guys in the bottom, and the literal unit on the right, below, it's going to wind up being on the right of the overall structure. If the points are in the bottom of one, they have to be on the top of the other, basically. And if it's at the bottom, then that means that literal will have the value of true. The next component are the consistency checkers, and those are to make sure that that those 2 literal units that we were showing before, they're going to be kind of across from each other. So one of them is going to shine into the left side, the F5, and then the other one is going to shine into F1. And if they're both on the bottom, which means that there's an inconsistency, then there's going to be both F5 and F1 are going to be seen. So you can't place another hidden point there. So in order to avoid that, you have to place the points at the top of 1 in order to place either at F1 or F5. And then F3 you can place regardless. And the last component is called the clause unit. And the clause unit represents each of the clauses. So each clause has 3 literals in it, and it needs one of them to be true to be satisfied. So if we have, previously in the literal units, each of those little bumps represented one of the clauses. And the idea is that if you have placed points in the bottom of those notches, those bottom notches, then you will be able to shine, then you'll, there's going to be one of these, either Q1, Q2, or Q3, depending on whichever one the literal was assigned to, they're going to be not seen. So maybe I should go back a bit. But, so these little notches up here, if you have a point at, say, Pn5 over here, then that point is going to shine into the clause unit, say, at Q3. If that point is up there, then that means that Q3 can't have a hidden point placed there. And if that is the case with all 3 of them, then the clause has not been satisfied. But if for any of the 3 there is, in one of the literal units, all of the points are in the bottom, meaning that that has been set to true, then there's going to be no conflict with putting a point into those into that slot. So the that clause will be satisfied since one of the 3 came back true. So this is the overall layout that Shermer gives, and I should mention that all of these figures are directly from the Shermer paper. And so on the left side we have the variables, or the variable literal units. That's just straight up the variable. If the variable is set to true, then those are set to true. Whereas the complemented variables, or the complemented variable literal units, are on the right, and those are the opposite. So if the component is, if the variable is set to true, then the literal unit corresponding to that variable on the right will be false. So all the points will be at the top. And there's a row of consistency checkers at the top to make sure that you don't have 2 set to false. 2 set to true. Both, like the variable is both set to true and false, but true in the complement and true in the variable. And they're both set. The bottom ones are to make sure that they're both set. They're not both set to false. So that makes sure that there's consistency in that way. And then the clauses are in the bottom right. And since there's a polynomial number of points in each of those structures, the total amount of hidden points, the total size of that structure will be polynomial. So it will be a polynomial construction of the of this gadget. And the way that you will be able to check if this 3-sat instance can be satisfied or not is whether the hidden set in total is equal to that which we would expect if all the clauses can be satisfied. All right, so that concludes our discussion of hidden set today. I hope that helped make the problem make a little more sense and make it a little bit more approachable. Have a great day.